Hey Rihan,
Hello, Brian.
how are you?
I'm fine. What's about you?
I'm doing fine too. I'm a little bit tired. I had a long day today, and last night I had a long review session. I think you saw the YouTube video, right? On the midterm review session that I had last night.
Yeah.
Yeah.
My exam is today.
Oh, your exams today? How are you feeling
Yeah.
for it?
I'm kind of nervous.
Kind of nervous. Is it gonna be on this stuff that you sent me on school, like this reaction right here?
Yeah.
Okay, yeah. There are a couple of reactions here that I don't recognize, like the CaC2 with water, so you could like walk me through it. Hey Jarrod,
Hello.
how are you today?
Good. I'm just preparing for the midterm tomorrow.
Oh, perfect for midterm tomorrow for 118B or for
For 118B, yeah, for
yeah.
Helix.
SCC 118B for Helix.
Yeah.
How are you feeling for it so far?
I think I have the mechanisms down. I'm just worried about the synthesis and then a little bit about the NMR.
Oh, I see.
Yeah.
Did you watch the review session that I made last night with the synthesis problems and all the predicted product problems?
I did a little
Uh-huh.
bit.
Yeah.
Yeah.
I see. Okay, okay.
Yeah.
So Rohan, we could go over like this crazy predicted product question with like a lot of steps, 24 steps. You can walk me through it. For like what's gonna happen between CaC2 and water? Like I have never seen this reaction before. Like
It will form ethine.
ethine.
Yeah, it is hydrolysis of carbide.
Oh, is it a three like double triple bond like that? Ethine, two carbon triple bond.
Yeah,
Ethine.
yeah, yeah,
Okay.
ethine.
Ethine. Okay. Okay. So ethine, we see that then it's gonna be reacted with H2 nickel.
Yeah.
What would
So
form in
ethane is
that
the answer.
case? Propane,
Ethane.
right? Okay. Now for propane, we're gonna react this propane with Br2 and light H nu. Okay. What is going to be formed from this reaction here?
It's put Cl on 2 degree carbon.
Yep. Let's put bromine on the second carbon. This is gonna be bromination. And from here, we're going to do this reaction here.
Is it ET1 a heat?
Yeah, it's gonna be
I think you made a
CH3
mistake in starting. It's not propane, it's ethane.
propane. Oh yeah, it's ethane, two carbons. Right, two carbons.
Yeah,
Right
2
here.
carbon.
Yeah,
Yeah.
right, two carbons.
Yeah. No put bromine.
Right, and bromine there, and then from here.
Next the reagent is Gilman reagent. You know this reagent?
Gilman reagent, yes. Gilman reagent is like a organometallic reagent, right?
Yeah.
Where it's R2CuLi.
Yeah.
And the
Now the
organ
propane will answer.
will be right there. Yes.
Yeah.
Okay. And then Cl2 new H nu.
Now put Cl on 2 degree carbon.
Okay. Cl right here.
Yeah.
And then next one we have
E2 mechanism.
Yep, V2 mechanism to create that alkene.
Yeah.
Next one, HBr with ROR peroxide.
Anti-Markovnikov.
Yep, anti-Markovnikov. Or like the thing you said, the Karsh. Is that
Harsh effect, yeah.
effect as well? Yep. Okay. And next one. What's this one? MgTHF to create Grignard reagent, MgBr. Yep. From here, we do first step CO2, second step acid workup to.
It will form carboxylic acid.
Yes, with the extra carbon, like that, carboxylic acid.
Yeah.
And then from here, NaOH electrolysis.
Electrolysis, Kolbe electrolysis.
Carbon electrolysis. Okay. This one here would convert the carboxylic acid to primary alcohol for hydrolysis.
It will form hexane.
Hexane.
Hexane, yeah. It will
One,
form
two, three,
hexane.
four. Oh,
No that carbon, only 3 carbon
3
with the
carbon.
mechanism of dot mechanism, free radical mechanism.
Radical.
Hexane.
Hexane. Hexane. 2,
Yeah.
3, 4, 5, 6. Hexane.
Yeah.
Okay, hexane. Okay. Next one, CrO3 TV
CR203. CR203.
CR203.
Yeah. It will form
And
benzene directly.
benzene.
Yes.
Okay.
6 carbon form benzene directly.
Okay. Is that TBLE as a solvent? Okay. So from here, that's the product of the first set of reactions.
Yeah,
Then-
this is P formed.
Okay. Next one is going to be C3H7.
7
Oh, it's H7.
7 Cl.
H7Cl AlCl3.
Yeah. It's Friedel-Crafts.
Friedel-Crafts alkylation. Yes.
It will form cumene.
Cumene. C3H7. Let's see. 1, 2, 3. 1, 2, 3. 4, 5, 6, 7. 1, 2, 3. Yeah. Propylite like that.
Yeah.
Okay. Next one. It's gonna be O2 and H nu.
Yeah. It will form hyperoxide
Peroxide.
in the middle of 3-degree carbon.
Okay. Can you send me that the name of the molecule? I don't know this reaction. Here.
Benzene hyperoxide.
Benzene. Okay. And what's attached to this benzene here? Hyperoxide. Benzene hyperoxide. Let's see what this is. Ah, I see it. Okay. Yeah.
No, this is not hyperoxide. This is wrong.
So what's the reaction, the product name? Benzene.
Wait.
Mhm. Do you mean benzoic acid? Like we have a carboxylic acid right here.
This reaction is called cumene hyperoxide rearrangement. You can Google it.
Cumene. How do you spell cumene?
Cumene hyperoxide
Cumene
rearrangement. Hyperoxide rearrangement.
hyperoxide rearrangement. Let's see. Yeah, I don't see the reaction clearly. So I'm not sure about this reaction too much. I haven't learned about this one. Yeah, sorry, Rohan.
You don't know the reaction.
Yeah, I have never learned about this reaction before.
So skip the next step. It will form cumene
Uh-huh.
hyperoxide. Then skip the next step. It will
Okay.
form phenol directly.
Phenol.
Phenol. Next
So
step is phenol.
like this.
O2
Phenol.
H2 plus H3O plus. Next reagent is H3O plus. Then it will form phenol.
Okay. So I'm gonna have you write it out in the whiteboard. So let's see here. Stop share. Let's put up the Zoom whiteboard and then you can draw it out. Let's see. Okay. Okay. Do you see the whiteboard?
Yeah,
Okay. Are you on your laptop or iPad or
iPad,
phone?
iPad.
iPad. Okay. Do you have Apple Pencil on your iPad?
No, I just
Let's
use
see.
fingers.
Okay, yeah. Try using your finger and see if this works. I've never used this tool before. This is like a new kind of whiteboard. Oh yeah, it works. Okay. Ooh, okay. There you go.
So this is benzene hyperoxide.
Benzene hyperoxide. Okay.
And when we hydrolyze it with acidic water, it will form phenol and plus acetone, right? No, this is the answer. Now move
Phenol.
on next.
Phenol is the answer after third
Yeah.
step. Okay. Let me screenshot this. Okay. Share screen. Yeah. So
Now next section is Ramer timer reaction. You know?
yep. So this one's gonna be right here. First step O2 H new. Second step acid workup to get to the phenol. Once we get the phenol, we react that with CHCO3
Yeah, Ramer timer reaction.
and AOH. So I've seen this reaction with alkenes. This is the 118B reaction where, like, if you react this with an alkene like this, you get the dichlorocyclopropane. But I
No,
have
we
not
don't
seen
have
it with
its
a
reaction.
phenol before.
In phenol, it will form salicylaldehyde. Salicylaldehyde.
Salicylic acid.
Like put CHO on orthocarbon.
Okay, aldehyde on orthocarbon.
Yeah.
Okay. OH, aldehyde on orthocarbon.
CHO.
Okay.
Yeah.
CHL. Okay. Next one. Is that H plus?
Yeah.
Yeah.
It's
Okay.
it's with Ramer timer reaction. Now
Dimer.
move forward.
Okay.
Now
H
next,
plus.
what is next reagent?
First step, second step. H plus.
Yeah.
H2 nickel.
H2 nickel.
Reducing agent.
Yeah, reduction.
Yep. So reduce aldehyde to alcohol.
Yeah.
Okay. Yep.
Yeah.
And then HClZ and CO2. ZnCl2. Okay.
Do you know this reaction? It's Lucas test.
No, I have not learned about this reaction too.
It will,
there is.
You see 1 degree alcohol, it will convert it into 1 degree chlorine.
1 degree
Put
chlorine.
chlorine.
Okay.
Yeah.
Oh, so yeah, this is nucleophilic acid with HCl. Yeah. So this
It's
is
called Lucas test.
Okay.
Yeah.
Next one. Zinc with H plus. Okay. What
It
will
will
this one
remove
do?
chlorine. It will remove chlorine.
Okay. Okay. Next one. Zinc dust.
Now it will remove oxygen.
Okay.
Toluene is the answer.
Remove the whole alcohol away.
Yeah.
Okay. So
It's just remove oxygen, so toluene will be answer.
Like that.
Yeah.
Okay.
It's called toluene.
Toluene.
Yeah.
Next one is KMNO4.
It's oxidative ozonolysis for KMNO4.
KOH, and that to create carboxylic acid.
Yeah.
Okay. Next one, SOCO2 to create acyl chloride.
Yeah.
Okay. Next one is phosphorus, AlCO3. Okay, what would that one do?
No. Yeah.
Yeah, what would this do here? The acyl chloride with phosphorus,
like-
AlCO3.
It's like Fiddler Cup.
It's like Friedel-Crafts. Okay, so we'll add phosphorus and substitute it with chlorine.
It's not phosphorus, it's P, it's benzene. We formed earlier.
Oh, that's benzene? Oh, this
Yeah.
is benzene?
Yeah.
Oh, okay, benzene. So this
Yeah.
is gonna be
I don't know the name of the product.
adding benzene to the meta position. Like that. And next one, zinc, mercury, HCl. Last one.
No, it's wrong. It's wrong.
So what should the product look like from here? Okay, let me put on the whiteboard
It's
again.
biphenyl. It's biphenyl ketone, I think.
Whiteboard. Okay. Yeah, let's draw it down below this work right here. I think you could scroll the whiteboard down. There we go.
I can show you mechanism either if you want. But this is the answer.
Yes. So that one attacks the acyl carbon and kick out the leaving group. Okay, got it. Yeah. Nucleophilic acyl substitution. Oh.
Now add the zinc HDSL. You know zinc HDSL what is? It's Clemmensen reduction.
Clemmensen reduction to get rid of the carbonyl.
Yeah.
Into the alkane.
Yeah.
Yep.
This is the answer.
Oh, okay. This is the final answer after the 24 steps.
We asked what are the number of resonating structures in Q. The final product found.
Resonance structures of this?
The number of RS.
So the benzene here can do resonance by itself. The resonance here can do resonance by itself, but they can do resonance with each other because of that sp3 roadblock. Right. So those two resonance structures, I mean these two benzene rings here can't do resonance with each other because of this sp3 carbon right there. Right.
Yeah. So answer is 4.
4. Yes. 2 from here, another from here. 4. Yep.
Yeah.
Okay. Nice. Yeah. Okay. Hey Jarrod, for 118B, did you want to go over specific synthesis problems or predictive products or how to approach spectroscopy problems?
Did you or could we do like a one synthesis and then like one like NMR, I guess?
Yeah. Let's do one synthesis problem and then an NMR problem using the winter 2023 practice exams or 2024. Have you tried out those exams yet?
From Helix himself?
Yeah, from Helix.
Yeah, I did both of them.
The 2023 and 2024 sections like A, B.
I think so. Yeah. The one that he provided in.
Oh, on Canvas.
Yeah.
Okay. Yeah.
On Canvas. Yeah, 24. Yeah.
Right. I see. Okay. We'll do the 2023 ones after the synthesis right here. Right.
Okay.
Yeah.
Okay.
So let me create a synthesis problem. This. Okay. Let's say. And this. Okay. Coming from yes, right there. Okay, let me see if this would actually work. That one, and then this one.
Oh.
Go all the way, and then this one, and then this one. Okay, 1, 2, 3, 4. Okay, yeah, this one here would work.
Okay.
Mhm.
So, I mean, what I'm thinking is I just know that there's an OH and there's
Mhm.
like some kind of like nucleophile, right? So like it's probably
Yeah.
like an epoxide opening with like acidic stuff, right?
Yeah,
But
so it would be epoxide opening, where the epoxide is gonna be like, let's say right here, and that's the OH part
Mhm.
of this molecule, and because that's a wedge, this epoxide here came from a wedge like that, and the methyl here is gonna say it's a dash. But we say that the nucleophile here, the OR, attacked the less subside of the epoxide, right? And when we open up epoxides, do you know the differences between opening up in acidic conditions versus basic conditions? Like which one would attack the more
Oh,
subside versus less subside?
I,
Uh-huh.
f- I think, shoot.
Yeah.
I think, is it base less
Mm-hmm.
substituted?
Yeah, basic conditions is
Substituted.
gonna be less substituted side, right? Mm-hmm. Right. So the first step is gonna be that ethoxide with its protic solvent, which is going to attack this less subside, invert the stereochemistry, kick that out to get this OR right there. That is a dash, right?
Mhm.
And then when this gets kicked off into O minus, that O minus can get protonated to OH using acid workup, H3O plus, like that. Okay,
Mhm.
yeah, so let's go backwards.
Okay.
Mhm.
And then, so I guess there has to be an alkene there in the first
Yep,
place. So there has to be like a MCPBA or something.
yep, right. MCPBA, which would make an epoxide from that alkene, correct?
Mm-hmm.
Uh-huh.
Let me look.
Yeah. And then once we get stuck here, you could think about going forward. Like what reactions would go forward.
I'm sorry. I'm looking at my like.
Uh-huh. No,
Yeah.
no card?
I'm looking at my like reaction thing right now.
Oh my god, you drew it all out on the whiteboard?
Yeah.
Oh shoot.
Uh,
Did you write out your note card yet too?
no,
Do you have that
no.
ready? Not
I
yet?
need to.
Okay. Wait, what time's your exam tomorrow? I heard people had it 1:40 p.m. today.
Yeah,
What time?
or one. Yeah, no, that was section A. So this is section B. So
Section B, yeah.
yeah.
Is
So
it the same time, 1:40 p.m. or is it like a different time?
1:10. Let me see.
Oh,
Let me see.
1:10 p.m. I see. Okay.
I think so.
Uh-huh.
It's probably 1:10. Yeah.
Okay. So you got some time in the morning to study.
Yeah. Is it? Shoot. Is there like?
So I'll give you a
like,
hint.
Hmm?
The first step, we have a carbonyl with an oxygen here. The
Oh,
first
is
step
it
is gonna be
It's a reduction, right?
yes, reduction.
ALH4, right?
You could either use LiAlH4 or NABH4, doesn't matter,
Yeah.
but it would be reduction using a reducing agent. Second step, acid workup to convert that carbonyl
Yeah.
into an alcohol like this. Yes.
And then it will be like a dehydration or something.
Yes, alcohol dehydration. Yes,
Okay.
with H2SO4 and heat. Yeah. So this synthesis problem, to summarize, first step was the reduction, second step alcohol dehydration, third step epoxidation with MCVBA, and then the last step was epoxide opening in acidic basic conditions.
That's good.
Right.
Can I take a picture of that?
Yep. So there were two 118A reactions here, the first and last steps, and then the two 118B reactions were in the middle. Alcohol dehydration. Maybe you learned alcohol dehydration in 118A.
Right?
And the MCV. Oh, wait, actually, like I think you've seen these reactions in 118A before too, like the MCVBA. Like who did you have for A? Whey or Farhat?
I had whey.
Whey. Oh, okay. So maybe she showed you this already too.
Yeah. But
Right.
she didn't show the mechanism. So
Yeah.
I mean, I think that was really helpful.
That's good.
I think what I'm confused about is
Yeah.
like the double bromide, like the what's it called? This reaction, the how the two Br2 like or like a like double halogen like reaction,
Yes.
and how that like the ring opening or for the bromium ion. I don't know like because I'm confused which because I know that like nucleophiles are attracted to more partially positive things, right? But then bases are like attacking less substituted, right? So
yes.
So I'm not sure like which one to like
to attack, like why does it attack the more subside in that rhodium ion ring?
Yeah.
So in basic conditions, think of it as a negative charge condition or neutral conditions, right? So if you look at this epoxide right here, there's no positive charge. Everything is neutral, right? So we know we're in basic conditions because of that negative charge right there, which is going to attack the less substituted side because of steric hindrance, right? So think of this as strictly SN2 reaction. It's going to go for the less substituted side and also invert stereochemistry. So this OR minus here is going to attack that less sub side right there because that's the most available side, the one that has more space for that nucleophile to approach, to come in and attack. And it would also do an SN2 backside attack like that. Right.
Oh, so you're saying so you're saying because it's neutral, that's why it doesn't what's it called? There's no partial positive or partial negative, right? Because
there's no full positive charge, right?
Yeah.
Because you can either have this neutral epoxide right here, or if you have acidic conditions like H2SO4 with CH3, CH2OH, the very first step is to protonate this epoxide oxygen right there, right? Because we have a strong acid present, sulfuric acid, right? And then when we protonate that epoxide oxygen right there in acidic conditions, we see that that ring, specifically this epoxide ring, now has a full positive charge right here. And when you see a full positive charge in the three-membered ring, you know you're in acidic conditions, right? And in acidic conditions, think of this as a good leaving group right now. And there's two ways that it could kick off. We could kick off the ring this way, forming a carbocation here, which is going to be, let's say, a tertiary carbocation, or we could kick off the ring this way, forming a secondary carbocation. Which one would you say is more stable here?
Tertiary.
Yep, tertiary. So the more substituted position, there's a bigger positive charge living in there because there is more stability there. And at the left side, there is a smaller positive charge living in there, right? So when we bring in our nucleophile, whatever it is, water, alcohol, it's attracted to the more subside because there's a bigger positive charge there, right? So the mechanism here is a mix of SN1 and SN2 properties. The SN1 property is that it attacks the more subside because of the more stable carbocation or positive charge. And then the SN2 property is the backside attack when we invert stereochemistry like that. When we invert this wedge bond into a dash bond. That's the SN2 property of it.
That makes sense.
Right.
So in like oxymercuration, demercuration, it would follow like the SN2, like
yes.
Okay.
Correct, because oxymercuration, demercuration, we have this mercuric ion specifically where you see that this mercury with 3 bonds, 1, 2, 3, has a positive charge, right? And we can think of it as the same way. If we have a positive charge here, think of it as a leaving group where the more subside will have the bigger positive charge, the less subside will have the smaller positive charge, which is why if you have water or alcohol, it's Markov-Markov addition. We attack the more subside because there's a bigger positive charge right there, living in there, right? Yes. So whenever you see a 3-membered ring with a positive charge, always attack the more subside. But when you have a three-membered ring with no positive charge and the nucleophile is strong enough to attack it, then we go strictly SN2, attack the left subside.
Mm.
And
Okay.
you'll most likely see a three-membered ring with a positive charge where you're gonna attack the more subside anyway. Right, because all the examples I've seen, even the open up epoxide ones, he opened it up in acidic conditions, which had the OR on the more subside and the OH at the less subside. I just gave you this one just in case it shows up on this exam, this upcoming exam. Right. Great. Okay. So
You have another one, or
yeah, I
okay.
wanna go over what 8B reactions first, and then we could go over spectroscopy at the end, like my approach on spectroscopy problems for 120 and 23. Right, but while we work on what 8B problems, I'll give you another statistics problem to try while I work on what 8B, right? Okay, this is just finishing off the mechanism here. The last step, HSO4 minus deproteinate.
It's the H.
Yeah, make it stable like that. R OH. Okay, so I'm gonna use one of these things here. Let's do this. Okay.
Ooh.
Boom. 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 Okay. Yeah, this one here is a little bit shorter than the last one. But this one here is gonna be doable here.
Okay.
Try this one out, and I'll go back to this question with you at the end of Alpha Stars. Okay.
Okay.
Yeah. Hey Jenna, hey Madison. How are you guys feeling about this Friday's quiz, this week's quiz so far for 8B?
Not bad.
Okay.
Okay.
That's good. What is it on again? Ether reactions, alcohol reactions?
Ether, redox of alcohols, epoxides, and aromatics.
Oh, okay. Aromatics, yes.
That's the part I'm most confused on.
Okay. Madison, do you want to go over aromatics as well? Does that sound good with you too?
Yeah, I was thinking I was gonna ask you about going over aromatics.
Aromatics, okay, yes. Okay, so for aromatics, there's three different types, right? The molecule can be aromatic, anti-aromatic, or non-aromatic. So I'm gonna teach you guys what I know about it first before looking at Levin's notes, and then I'll check Levin's notes after to see if I'm missing anything that she wants you guys to know. Right. Okay. So the most common aromatic molecule that you guys have seen is a benzene ring, like this. Right? A six-membered carbon ring with alternating double bonds like that. This benzene ring here, because it could do a lot of resonance around the ring, like a lot of resonance, makes that structure stable. Right? And if it's stable, it is less reactive. Right? You could think of it as unreactive. So even though there are three alkenes in here, when we try to do an alkene reaction, like let's say HBr, no reaction happens because these double bonds here don't want to break. They don't want to break the stability, so they are going to do no reaction. But let's say you have a six-membered ring here with one alkene and you react it with HBr, that would do a reaction because this one alkene here is not aromatic, right? It's not doing resonance with any other double bond. It's localized, it's stuck right there. And because it's not doing resonance, right? There's less resonance here, less resonance. That would make it less stable, aka more reactive, right? And because it's more reactive, it's able to react with the alkene reactions that we're used to seeing. Okay. Now let me show you guys this table that I use to determine whether a molecule is aromatic, anti-aromatic, or non-aromatic. To be considered aromatic or anti-aromatic, you need to fulfill all three of these conditions. The first condition is that it has to be cyclic, right? The molecule has to be cyclic in a ring. The second condition is that it has to be fully conjugated, meaning that it could do resonance all around the ring, right? If it could do resonance partially throughout the ring, but not all the way, then it's not going to be aromatic or anti-aromatic. And then the third condition that the molecule has to fulfill is that it has to be flat and planar. Everything has to be onto the plane of the page or the board, right? So let's say the molecule doesn't fulfill one of these conditions, like it doesn't fulfill the cyclic condition, fully conjugated addition, or planar addition. As long as it doesn't fulfill one condition, then it is automatically considered non-aromatic, right? So once you find out that the molecule does not fulfill one of these conditions, then it is automatically non-aromatic. So missing one or more conditions. Okay, so now let's say it passes all of these three conditions. To tell the difference between aromatic and anti-aromatic, we then look at how many pairs of electrons are involved in the resonance, right? This is when we bring in the 4n plus 2 and 4n rule, right? So the 4n plus 2 rule and 4n rule is just talking about how many pairs of electrons are doing resonance. And n is any non-negative integer, like 1, like 0, 1, 2, 3, 4, 5, any whole number like that. So an aromatic and anti-aromatic, what I like to think about instead is that aromatic structures will have an odd pair of electrons, whereas an anti-aromatic molecule will have an even pair of electrons, right? So let's look at this classic example of a benzene, right? So whenever you're given a molecule like this, first see if that molecule fulfills all three conditions. This benzene is cyclic because we have a full ring here. This molecule is fully conjugated because we see that these double bonds in the ring can do resonance all around with each other. So it is fully conjugated. And it is planar because every single atom in that ring is double bonded and sp2 hybridized. And sp2 carbons are flat, right? And if they're flat, they are also planar. So it fulfills all three conditions. So we know that this molecule is not non-aromatic. It's either going to be aromatic or anti-aromatic. Okay, so once we find out that this molecule fulfills all three conditions, then we count how many pairs of electrons are doing resonance, right? We have 1, 2, 3 pairs of electrons, which is an odd pair of electrons, right? An odd pair of electrons associates that with aromatic molecule. So this benzene here is aromatic. If you want to think about it in Levin's vocab terms, just in case she asked about this 4n plus 2 for n rule, this 4n plus 2 is basically meaning there's like since there's 3 electrons, 3 pairs of electrons, there's 2, 4, 6 electrons doing resonance in total, right? Because 3 pairs, 3 times 2 is 6 electrons. And this 6 electrons falls under the 4n plus 2. Because if you plug like a random number here, it's going to be equal to 6. In this case, n is equal to 1, right? Because 4 times 1 is 4, 4 plus 2 is 6. So that's more abstract way. That's why I don't like thinking about it like that, because you have to plug in random numbers for n, like 0, 1, 2, 3, just to match how many electrons are doing resonance with each other. So I don't like thinking of it like this. But this could show up in vocab, so just be familiar with it, like what it means. Right? But if you're just identifying what the molecule is, aromatic, anti-aromatic, or non-aromatic, you could just think of it as how many pairs of electrons, an odd pair or even pair, are doing resonance with the ring like this. Right?
Could you maybe give another example for like finding electrons, like how many electrons there are?
Yes, of course, of course. Let me pull up a lot of examples for you, which is going to ask you to determine if the molecule is aromatic anti-aromatic or non-aromatic here. Okay. 118B. This one. Let's go down. Okay, so this is a 118B reaction, which it's midterm 2, midterm 2 material. But for 8B, it's gonna be quiz 2 this Friday. And show you guys this right here. Okay. And there are like a couple of examples that I want you guys to be wary about as well. Right. Let's start off with the carbon ones because you could have heteroatoms, which means like the rings can have non-carbon atoms, and that would make things a little bit more tricky. Right. That's one. That's another one. This is another one. This is another one. This is another one. This is another one. Okay. Let me give you some heteroatoms in here. Let's give you this one. Let's give you this one. Let's give you... Yeah, let's give you 2 more examples here. 2 more weird examples to look out for. Ooh. Okay. Let's see here. There we have. Okay, we'll alternate between Madison and Jenna. Madison, I want you to determine if this molecule is aromatic, anti-aromatic, and non-aromatic here. Right. So what would be your thought process on how to do that?
Well, just going down, like first doing my eliminations of deciding if it's cyclic, fully conjugated, and planar. Planar.
Right, planar, right?
Is it cyclic?
Yes, it's cyclic.
That's because all the bonds can do resonance with one another, correct?
That's the fully conjugated one, right? Where all the double bonds here can do resonance with each other. That's fully conjugated.
Okay.
Right? That's the fully conjugated one. It's fully cyclic because you notice how they're doing resonance in rings like this. They're all in a closed ring like that. That's the cyclic part. The fully conjugated part is when they can do the double bonds can do resonance around each other like that, all around like that.
Okay.
Right. So cyclic, fully conjugated.
Planar.
Planar, yes, it's also planar because all atoms in the ring here are sp2. Right. Okay. Once we have those 3 conditions filled, would you say this is aromatic or anti-aromatic? How many pairs of electrons are doing resonance here?
1, 2, 3. Isn't it anti because it's 6?
6 pairs of electrons, that's an even pair. And an even pair, we said, is going to be anti-aromatic. This is anti-aromatic, yes. But if you want to do the 4n plus 2 and 4n rule, anti-aromatic is going to have 4n electrons, right? Because it has 6 pairs of electrons, it's going to be 6 times 2, which is 12 electrons, right? So n here would be equal to 3. N is just random number that you just plug in to satisfy how many electrons are doing resonance here. So yep, this molecule here is anti-aromatic. Nice.
Okay.
Okay. Next one. Jenna, would you say this is aromatic, anti-aromatic, or non-aromatic?
Okay.
Mhm.
I would say I kind of already went over this with somebody earlier. I would say that it's not because there's an sp3.
Yes, there is an sp3 roadblock right there.
Yeah.
Right? And that sp3 atom, whenever you see an sp3 atom in the ring, blocks resonance, right? This double bond here cannot do that. It can't make a double bond right there, and that double bond cannot go there. Can't do resonance right there. Right?
Yeah.
It is cyclic, right? Because it's in a ring, it's cyclic, but it is not fully conjugated. It's partially conjugated. It could do resonance like this, right? Or like this with each other, but it's not fully conjugated. It can't go all around the ring like that. And because it's not fully conjugated, automatically non-aromatic.
Okay.
Yeah, you got it.
I think I understand the conjugation part. Like that's just p orbitals that are constantly like rotating and switching, right?
Yeah.
What-
Because
Okay.
when you see these alkene carbons right here, they're sp2 hybridized, and all sp2 carbons would have these p orbitals here that are dumbbell shaped that are gonna overlap with each other like that in parallel. Like
Yeah. And because that point at the top doesn't have an alkene, it's going to be sp3, and we don't have a p orbital for it to be fully conjugated and to be fully rotating.
Yes. That's
Okay.
correct. And it does not have to be an alkene, right? Because a carbon with or an atom with a pair of electrons or a positive charge, like a carbocation, can have a p orbital as well.
So the one, actually, I don't know if I won't give the answer for the next one.
Okay, yeah. So let's see here.
I actually had one question before that. Levens did say that if we were to draw like a mechanism of aromatics, she would want to see all of the resonance structures, but like I don't know what that would mean.
Yeah, so there are, like, if we want to draw out the resonance structures, I'll start drawing it on the next one, and then I'll show you like what the possible ones could be here, right? Okay, yeah. Madison, would you say this is aromatic, anti-aromatic, or non-aromatic here?
I think it's anti or non.
Non, and what condition is not fulfilled here if you say it's non?
I think it is cyclic.
It is cyclic.
I don't think it's fully conjugated.
And why do you think it's not fully conjugated?
Well, it's similar to the previous one. I mean, but we do have that
negative charge, right?
Yeah.
And when you see a negative charge on the carbon, there is an invisible pair of electrons right there, right? And that invisible pair of electrons is in a p orbital like that, right? So this carbon here is sp2 hybridized, not sp2, not sp3, right?
Yeah, not like the previous one.
Right, because when you see a carbon that's double bonded, or a carbon that's negatively charged, or a carbon that's positively charged, all of the green carbons right here that I'm color coding are sp2 hybridized with a p orbital, like that.
Okay.
Right. The double bond carbons are sp2 hybridized. The carbon with the negative charge is sp2 hybridized, and the carbon with the positive charge is also sp2 hybridized right there.
Oh, I see.
Right. So let me draw that out like this. The alkene sp2 are, like, those p orbitals are parallel overlapping to create that double bond right there, to create that pi bond.
Right.
Pi bond. The negative charge has a full p orbital with a pair of electrons on that p orbital right there, because it's negatively charged. The positive charge is going to have an empty p orbital. There's no electrons in there. That's why it is electron deficient and has a positive charge, because it's missing electrons. There's still a p orbital there, like this p orbital, but it's empty. This is an empty p orbital. No, nothing in there. right?
Okay.
And that's why it has a positive charge. There's a void in there, no electrons in there, right? Okay. Now, because we have this carbon with a negative charge right here, that is sp2. It is now fully conjugated because it could do resonance all around the ring right here. Right now, I'll show the resonance structure after, but it is also planar because all the atoms are sp2. Now, how many electrons here would you say are doing resonance with each other? How many pairs of electrons?
It would be 3.
3 pairs. That would be an odd pair, which is aromatic.
Okay.
Yep. Right. Now, let me show you the fully conjugated part of this, which was showing you the resonance structures. If we know that this carbon here with a negative charge has a pair of electrons, that pair of electrons here can make a double bond right here. Right. But that's going to break the octet rule for this carbon because this carbon already has 4 bonds. 1, 2, 3, 4. And we're trying to make another bond here. So that's going to be 5 bonds. That's not good. We don't want that.
Right.
So to conserve the octet rule, we have to break this double bond and go to that carbon right there. Right. So let me draw that out and show what that means. So if we move that pair of electrons to make a double bond right there, this double bond can no longer be there to conserve the octet rule. And this bond here has 2 electrons. Those 2 electrons are going to move and land on this carbon right there, giving that carbon a negative charge like that.
Oh, I see. Okay.
And then we could do the same, make a double bond there, and move that double bond to give that carbon a negative charge right there. Okay. And in resonance structures, charges are conserved. We have to maintain the same charge for all resonance structures. Negative charge, negative charge, negative charge. They're just moving around the ring.
Okay. That makes sense.
Yep.
I see.
Yeah. And that's how we could draw the resonance structures from this structure here. And be careful here, when we draw resonance structures, the arrows always start from a negative charge, like either a pair of electrons like that or a double bond, towards something that is like positively charged, where the electrons are going to. Right? You never want to draw something like this. Like if you have something like this with a positive charge, we don't want to draw the positive charge moving there because there's no electrons there. Right? There's nothing to move there. So we never want to draw an arrow starting from a positive charge. Right? We can start either from a double bond or a pair of electrons like that. Okay? Nice. Did that make sense, Madison?
Yes.
That's good. Okay. So let's move on to the next one right here. Jenna, would you say this is aromatic, non-aromatic, or anti-aromatic?
That one would be so it's cyclic.
Cyclic.
It's also sp2 hybridized.
All around the ring, so fully conjugated.
Yeah. So that means it's also planar, right?
Yep, planar. There are some cases where Leibniz wants you to know where even though it is cyclic and everything is fully conjugated, sp2 hybridized, there's some examples where it's not planar because of the geometry. Like it's too bulky, it like makes a boat shape, it bends itself. So those are like the memorization molecules, I would say. And I give you guys 2 memorization molecules. I want you guys to know that even though it is cyclic and fully conjugated, it's not planar, right?
Okay.
Yeah, but this one here would be planar.
This one's planar.
Yeah.
But because it has a positive charge, it would only be 2 pairs of electrons, and that's even. So that would be anti-aromatic.
Correct.
Okay.
Yeah, you got it. Right. The 2 pairs of electrons are coming from these 2 double bonds here, and this positive charge here does have a p orbital, but it's empty. There's no electrons in there. Nice.
Yeah.
Okay. Okay, Madison, let's try this one.
Okay. This one, is it cyclic?
It is cyclic. Yep.
Okay. So it is cyclic, fully conjugated.
So this one here is a bit tricky. What is the hybridization of these carbons here? The one that has no double bond, no positive charge, no negative charge. It has 4 bonds.
Is that SP?
SP3. SP3.
Is it SP3?
Yes. these carbons here are sp3 carbons. Because there's no double bond there, there's no positive charge there, there's no negative charge there. And this carbon here has 4 bonds, right? 1, 2, 3, 4. The other carbon also has 4 bonds. 1, 2, 3, 4. And the carbon with 4 bonds is sp3 hybridized, right?
Oh, okay.
So this negative charge here, right, is sp2. The one on top is sp2. Because it has a full negative charge or a pair of electrons in a p orbital like that, a full p orbital. But those 2 electrons, that pair of electrons, cannot do resonance at all. It can't go down there, it can't go down there.
Right.
Because these sp3 roadblocks here are blocking the resonance.
Right, because they're already fully bonded.
Yes, they're already fully bonded and it can't gain another bond, right? Because there's nothing to kick out. Even if we try to make that double bond right there, we're going to break the octet rule on this carbon. We can't kick out a hydrogen. We can't kick out that hydrogen. We can't kick out that carbon bond, right? But in the previous example right here, we saw that even though this carbon also had 4 bonds already, 1, 2, 3, 4, we can, like right here, 1, 2, 3, 4, we can make a double bond right there, which then we will have to move another pair of electrons to conserve the octet rule. And we can move that double bond onto that carbon right there, right? But if we go back to this example right here, there's nothing to move when we try to make a double bond right here. There's nothing to move. We can't move hydrogen bonds or carbon bonds like that. No double bonds there to move.
So then it would break it would be missing essentially a condition.
Yes,
Okay.
Non-aromatic, correct. And the condition that it breaks is that it is not fully conjugated, right? Not fully conjugated. Okay, nice. Next one, let's try this one.
Wait, before we move on to that, I missed the last part. Were you saying that it's not fully conjugated because we have those sp3 carbons, so we would need all of them to be sp2 in order for them to be fully conjugated?
Yes, all of them in the ring has to be sp2 to do full conjugation. And full conjugation is another way of saying doing resonance all around the ring. And to do resonance, you need a p orbital, like a dumbbell-shaped p orbital to do resonance, right? And those p orbitals come from sp2 carbons or sp carbons.
Yeah.
With the triple bond. But these sp3 carbons here have 0 p orbitals. They do not have those p orbitals right there. And because they don't have those p orbitals right there, electrons cannot flow there. Electrons cannot flow in that molecule, right?
Okay, that makes sense.
Yeah.
The next one, we know it says 8 carbons, it's cyclic.
Cyclic. So this ring here is 1, 2, 3, 4, 5, 6, 7. 7-membered ring.
Oh, 7.
7.
But we don't have p orbitals all around. Or no, we do.
We do, right? Because this carbon here with the positive charge does have a p orbital there, but it's empty. There's a void there. There's nothing there, because there's a positive charge right there. Like whenever you see a positive charge, it's electron deficient. It's missing electrons. Right? But there is still a p orbital there.
So even if electrons are missing, a p orbital still exists. It's just okay.
Correct.
And then that still makes it conjugated?
Yes, it still makes it fully conjugated, because if I were to draw you out the resonance structure for this one, which is going to be good practice for this quiz as well, we cannot move the positive charge around like that, right? But we can move the double bond around. So let's say that we move a double bond over to make a double bond right there. When we do that, we're going to get this resonance structure here, where the double bond is now over here. And because this carbon here gained a bond, it's now neutral, right? This carbon is now neutral.
Yeah.
But this carbon right here lost a bond when we moved that double bond away.
Yeah.
So because this carbon lost a bond, it's missing 2 electrons. That carbon will now have the positive charge like that. Right?
Oh, okay.
And that conserves the charge.
Yeah.
This carbon here has 4 bonds, and it stays as 4 bonds when we move that double bond like that. So it stays the same, stays neutral.
Okay. That makes sense.
Okay, because we're filling in this void to create another void right here.
Yeah.
Right?
Okay.
And then we can keep going like this. If you want to draw out all the resonance structures.
Okay. Yeah, I don't know how she's expecting us to draw all of them when we only have 20 minutes.
20 minutes? Oh my gosh, yeah, it's so fast.
Yeah.
Like you gotta like write everything so fast, no time to
Yeah.
check your answer, and just go like if you get stuck on something, move on and like
Yeah.
try to get
Yeah.
the next one, you know? And then when you have time, hopefully you have time, go back and try to try to solve it.
Exactly.
Yeah. Did she post the practice quiz yet for this
Yeah,
quiz?
she did. She has all of them.
Yes. Okay. Yeah, we could go over that tomorrow and Thursday, office
Yeah.
hours. That practice quiz. Yeah.
Um.
Okay.
So we know that it's fully conjugated.
Mm-hmm.
All the resonance.
Mm-hmm.
It's cyclic.
Mm-hmm.
And it's planar.
Yes.
And we have 1, 2, 3. That's odd.
Odd pair.
Aromatic.
Aromatic. Yes. Uh-huh. And a lot of people get confused about the odd and even pair because when you think about the stability of these things, aromatic is the most stable. Right? The non-aromatic is in the middle. Then anti-aromatic is the least stable out of all of them. Right? And people associate aromatic with even numbers sometimes because they like even numbers better. It's a nicer number, right? But that's wrong. Like it's an odd pair of electrons for aromatic, and an anti is an even pair. Right?
Okay.
Yeah. Nice. So odd pair, as long as you fulfill all three conditions, aromatic. Okay. Now the next three sets here are going to be a little bit confusing because we have a hetero atom now, a non-carbon atom, which is nitrogen in this case, right? So, Madison, for this one, I'll have you try it first. It's okay if you can't get it. Let's see what you can do here first.
Okay. So, is it cyclic still?
Cyclic still.
Okay. Fully conjugated, I want to say.
Yes, fully conjugated, right?
Because it can still like move around.
Yep. This nitrogen here is neutral, has an invisible pair of electrons. On the quiz, she will not draw this pair of electrons out, but that is the one that is doing resonance around the ring.
Around the ring. Okay.
Yep.
So it can still move around this
Yep.
pair of electrons.
Right.
Planar.
Planar, cyclic, fully conjugated. All three conditions fulfilled.
So then it would have 1, 2. Is it just 2? 3. Wait. It's
so 2 from the double bond, and the third one is from that pair of electrons.
Pair.
Oh, nitrogen right there. Yes, 3 pairs.
Okay. So then it is aromatic.
Yes. You got it.
Huh.
Yep.
Can I ask why? So it still is sp2 hybridized with that nitrogen?
Yes. And that's a good question because if we have, let's say, just focus on this molecule here with a nitrogen and 3 bonds and a pair of electrons like that. This itself, where this pair of electrons cannot do resonance at all, like it can't move here, it can't move there, it can't move here. This nitrogen atom is sp3 hybridized, right? Because there's 4 bonding groups attached to it. 1, 2, 3, 4, sp3 hybridized, right? But when that pair of electrons can do any sort of resonance, like let's put a carbonyl here, a carbon double bond oxygen, we see that this pair of electrons can do resonance with the carbonyl like that. Right? And if I draw out the resonance structure of that molecule, I'm gonna get this resonance structure here. Right? Where the oxygen will have a negative charge because it gained a pair of electrons from this double bond. And this nitrogen is now positively charged because it has 0 pairs of electrons and 4 bonds. Right? And if you calculate for more charge, nitrogen is on the 5th column, 5th group of the periodic table. We subtract how many electrons it has to itself. It has 1, 2, 3, 4 electrons to itself. So 5 minus 4 is positive 1 charge. Right? But the most important thing here is that if you look at this resonance structure, it has 3 bonding groups. 1, 2, 3. And those 3 bonding groups makes this nitrogen sp2 hybridized. Right? So in the first resonance structure, it looks sp3 hybridized because there's 4 bonding groups. 1, 2, 3, 4. But in the second resonance structure, it looks sp2 hybridized because there's 3 bonding groups, 1, 2, 3. So when this nitrogen here can do resonance, it's gonna favor the sp2 hybridized orbital over the sp3 orbital, because this sp2 hybridized nitrogen here allows for the resonance structure to occur. And we want the molecule to do resonance because resonance is a stabilizing factor. It makes the molecule more happy, more stable.
Okay.
Right? And to allow for resonance, we gotta keep this nitrogen as sp2.
Okay, got it.
Yeah. Right. So that nitrogen here is sp2 because the p orbital here holding those electrons are flowing with the other p orbitals around the ring like that. Right. Okay. Yeah. Okay. Nice. Okay. Next one. Here. This one's a little bit trickier.
Okay. So we have cyclic, conjugated. We also still have that lone pair
on the nitrogen right there. Yep.
So that could do resonance, right?
Yeah, so this one here is the trick, right? Notice how the nitrogen here is double bonded already. So this nitrogen will have a p orbital, right? But that p orbital is occupied by the double bond, right? This overlap between the two p orbitals here, where you see the double bond between carbon and nitrogen, right? That double bond right there, is this overlap between the p orbitals. And because of that, the pair of electrons here is in an sp2 orbital.
Oh.
So, when you see a pair of electrons on the nitrogen that's already double bonded, this pair of electrons here is in an sp2 orbital that cannot do resonance. Because electrons in the p orbital do resonance. Electrons in the sp2 orbital are stuck there. They're trapped there. Yeah. Okay. If you look at the previous example here, this nitrogen here was not double bonded at all, right? Let me draw out the structure out for you like this. This nitrogen here with the pair of electrons is on a nitrogen that is like all single bond, no double bond at all. So because there's no double bond, the p orbital is holding that pair of electrons, allowing for the delocalization or resonance around the ring like that.
Okay.
Yeah.
So the criteria for this to determine if a lone pair is sp2 or sp3 is to see if that atom is double bonded already.
Yes.
And whenever it's double bonded, that lone pair can't move.
Yes.
Okay.
Just like this one. Because this nitrogen is already double bonded, this lone pair cannot move. Right.
Okay.
But this lone pair right here on this nitrogen is on a nitrogen that is not double bonded. Right? There's single bond, single bond, single bond. So this can move around like that.
Yeah. Okay.
Right. Yeah.
So that would mean it's not conjugated because it doesn't have free rotation.
So this one here does not have free rotation, but it will still be fully conjugated around the ring, but between these 3 pairs of electrons right there.
Oh, because it's only well, they're all p orbital, right?
All of these are p orbitals right here, but they're occupied by double bonds rather than a pair of electrons floating on the nitrogen atom. Right.
Okay.
Right. Wait, my iPad. My laptop is 10%. Let me charge my laptop really quick.
Okay.
Yeah. Okay.
Okay.
Let's see. Okay, so we would say there are how many pairs of electrons doing resonance in this ring here?
0.
0. So these double bonds here in the ring are doing resonance. So it's those 3 pairs. 3 pairs. Right.
Oh, wait, I thought if there's that lone pair that can't move around, that means like you just can't do resonance, or is it just that lone pair alone can't do it?
Yes. This lone pair alone cannot do resonance.
Oh.
Right.
But double bonds still can do resonance.
Yes, these 3 double bonds here can do resonance.
Okay.
Right, like that.
So
Mhm.
that means we have 3 pairs of
Yes.
electrons that can do resonance. Odd, so that's aromatic.
Yes, that is aromatic. Right.
Okay.
Aromatic. And for this one here, I drew the same thing, but I wanted to draw out this one right here. Nice. You got that? Right here. Okay, let's try this one. Madison?
So that one is cyclic. It is that fully conjugated?
Fully conjugated, because there is a pair of electrons of this nitrogen right here. And is this nitrogen double bonded at all? No, it has single bonds. Single bond here, and single bond here. So because it's not double bonded, this would count.
So it still can freely move around.
Yes, it can still freely move around the ring. Yeah.
And then it is planar because everything looks sp2 hybridized.
Yep. Right.
And then so it has 1, 2, 3, 4, 5.
Yep.
So that is still aromatic.
Yes, you got it. Yep. Right. Okay. Now, the last 2 here, I'm just gonna tell you guys because if it fulfills all 3 conditions, right? These 2, it's cyclic. It is fully conjugated. It could do resonance all around the ring, and it is planar. Right. But because of the shape of this is the weird one. This is the exception. Right. This is non-planar. Non-planar. Right. Even though all atoms in the ring are doing resonance and are sp2 hybridized, these molecules are non-planar because this molecule here is very big, 8-membered ring. So it's actually going to be a boat shape like that. So I could see Levens putting a question on the vocab on why this structure here, even though it fulfills all 3 conditions. Oh no, not all 3 conditions. Even though all atoms here are like sp2 hybridized and can do resonance with each other, why is it non-planar? Right? Why is it non-aromatic then? It's because it is bent in this boat shape. Right? This is the boat shape here. Boat shape molecule. Which is not flat and planar, right? There's parts of the molecules are sticking up like that. Okay. The reason why this molecule here is non-planar is because of the middle right here. Like they're so close to each other that like one hydrogen is gonna become a wedge, another hydrogen is gonna become a dash, and so that like makes the molecule not flat anymore. Like this molecule would go up and the other molecule would go down. Right, so it won't be flat anymore. There's some bent shape to it, right? So when you see something like this, just know that that's non-planar, and so therefore that would be non-aromatic because it doesn't fulfill the planar rule. Right. So these 2 molecules here are non-aromatic. Right.
Are those the biggest exceptions that we should like? Is there a pattern for exceptions, or are they just kind of random?
They're kind of random. Like you just gotta like recognize them, know them. A lot of like bigger rings, like she'll say, is non-planar because those big rings tend to fold in a shape, right? They start to like acting linear because of less ring strain. So like these big rings like this tend to be non-planar. That's a pattern that you could see.
Oh, okay. That makes sense.
Right. But this one right here is because of steric hindrance right there. Nice. Okay. Yes. That is aromaticity. I'll look more on your Levens notes and then see what I'm missing and go over that tomorrow with you guys as well.
Okay. Thank you.
Yep, of
Thank
course.
you so much.
Yes, of course, guys. Okay. Gerard?
Oh, I didn't draw the whole thing. Okay, that's I'm so confused. I was like, okay,
Wait, what did you draw?
No, because I didn't put the methyl on the top
Oh,
of the product, so I was like, how the heck am I? Okay, okay,
Uh-huh.
so
Wait, did you draw the metal and the reactant? But you forgot to draw the
Yeah.
product?
yeah.
Oh, okay,
I was
yeah,
just like looking at it, I was like, wait, okay. So wait, I forgot what I was doing, but I think I would have gotten it. I would have gotten the thing if
yeah.
so. Okay, so is it shoot. Okay. Well, the BR has to be like a anti-Markovnikov, right? So it has to be like it has to be hydro like boration or something.
Yeah,
Or...
so I like what you're thinking about it. The BR is
Oh,
on the
no,
less
no.
subcarbon, right? So it is anti-Markovnikov. Like if you're thinking there was an alkene right
Sorry,
here, right?
HBr.
HBr with ROR
Yeah,
on
yeah,
OOR,
yeah,
right?
yeah.
But we also see an OR here next to it, right? And when you see a BR and an OR or OH next to it, it would actually be a different reaction, right? Because let me ask you this right here. If I give you this alkene and I react it with Br2 and water, what would you say the product is?
It attacks the more substituted, so it would be the with the OH, or it's like, is it like this? Or
yes, so OH
yeah.
would be on the more substituted side, and BR would be on the less substituted side.
Oh, okay.
Right.
Oh, yeah, the BR. Okay.
Because if we draw out the mechanism here, we're gonna form a bromonium ion ring. The carbon attacks that bromine, kicking out the other bromine. That bromine comes back to attack the other carbon at the same time, and that creates this three-membered ring with a positive charge. And water, because we see this positively charged ion here, is going to attack the more subside, because we said earlier that more subside has the bigger positive charge, right? Because it's more stable there.
Yeah.
So this is going to be oxonium ion, and eventually when we deprotonate it with another water molecule, it becomes neutral OH, like that. Right. It didn't have to be OH. If we had alcohol like ROH, then this would have been OR, like OCH3 or OCH2CH3.
Yeah.
Right. But you notice out here that when we see a bromine adjacent to like OH or OR, we're gonna do this X2 with water or ROH reaction. Right. So when we go backwards right here, our alkene is going to be this alkene right here.
Yeah.
Right. But the reaction here is going to be Br2, and because we have this OR right here, it's going to be CH3OH as the alcohol, right? Where we add the CH3OH on the Markovnikov position, the more sub position, having the bromine on the less sub position right there.
Yeah.
Right.
And then so forming the like a terminal. Okay, would you use like a oh, you have to OH it first, right? So you have to do acid with water, and
you
then
want to create an OH on this more sub position right here.
Yeah, and then butoxide, right? So that you have the
less stable alkene.
Yeah.
Yes. So we do want to do E2 Hoffman using a bulky base like turbotoxide, but we don't want alcohol here because that's not a good leaving group. Right? We want a good leaving group though, like bromine.
Oh, bromine. Okay. Okay. So it would be like a BR. HBr. Okay.
Yes. HBr. Right. Because BR would attach to the more subside and H would attach to the less subside like that. Right. So the first step was HBr. Second step E2 Hoffman. Third step was BR2 methanol. Right. Let's just go over one more here, and then I'll I wish you luck for your midterm tomorrow. For your midterm tomorrow. Yes. Let's see here.
I think I know the mechanisms. Mechanisms. It's just that it's hard to like do it backwards. You know what I mean? And think about like creative
synthesis going backwards. Yeah. It is because like, you just learn about this reactions, and then like you have to know the patterns, like know the reactions very well in order to like do the synthesis films, like going backwards and where things came from. Let's see here. Yeah. But That's good. Let's do this here. Let's say this. Okay, yep. And I want you to okay. And this reaction here, I'm gonna have you see if this works. Boom. 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 2, 3, 4 reactions here. Yes.
So, I mean, I see the Cl and the Cl, so there has to be a chloroform, like carbene, like reaction, right? So,
Yep.
And then, so then, I think it's the BR. So that BR has to be eliminated, right? So it's.
And do we want to eliminate it and create the double bond here, or do we want to create the double bond here?
The first option.
The first option, the more substituted option. So, what kind of base would we want to use?
Strong base, like sodium hydroxide, or
yep, a small strong base, like sodium hydroxide in water. We don't want to use turbotoxide or LDA because that would go for the less stable alkene, right? We want to create this more subalkene right there, right?
Yeah.
Okay.
And then, would you do like an acid in water so that? Oh wait, no. Would you do addition so that you or
so we're trying to convert this to this right here. Yeah. What reaction makes the less stable alkene right here? Because you see how here, if this pink carbon here was the shared pink carbon that had the good leaving group, right? Let's say bromine was right there, right? Like we added bromine there.
Yeah.
Because what reaction do you know that would add bromine to that pink carbon, to that good leaving group right there?
Wait, say that again. Or there, and
yeah.
then
Yeah. What reagent would convert this alkene to this bromine at the anti-mark position? I'll give you a hint. What sound does the lion make?
HBr and then the ROR. Right?
Roar. Yes.
Peroxide, right?
Yes. The peroxide, ROOR heat, which adds bromine to the anti-mark position, the less sub carbon. And from here, how can we convert this into this right here?
Let me see. Oh, that's so you would use like turbotoxide because you want to be less substituted.
Yes, turbotoxide, just like that, right?
Wow,
you got it. So first step was E2 Hoffman. Second step, radical addition of HBr. Third step, E2 Hoffman, and then fourth step was the chloroform that you got earlier, like that.
It's just, it's just really like. I'm just slow at it, you know what I mean? Like,
I know it's okay because you just learned about these reactions, you know. So, I would leave this at the end. Do all the predicted product reagents first because those reactions can give you a hint on what to use for the synthesis, like the predicted product reagents and reactant they give you. You could use some of those reactions as an idea, like if you could use those in synthesis.
Yeah.
You know, did you look at the winter 2023 section A and B exams that I sent out last night, or do you have access to that?
No, I to be honest, I just found your like YouTube channel like tonight.
Oh, you just found it like tonight?
I found it tonight. I was like, wait, this is amazing. Like, wait, why is this like helix?
Oh my goodness! Wait. So
the
one that you have for right now that Helix sent, on Canvas is the winter 2024 one, right? The two
Yeah,
section
the
A and
A
B.
and B, A and B. Yeah, that's it.
Yes.
Yeah.
I am going to send you winter 2023 section A and B, so you have more of idea of what Helix exams are like.
Thank you so much.
Yes.
Yeah.
And then you could like, do practice with predictive product and synthesis on Helix style questions, right? So then like it's gonna be very similar to the exam tomorrow, right?
Thank you so much.
Yes, of course, of course.
Yeah, I have to come back. Like, you know.
Yes, yes. Let me know how the midterm goes tomorrow too. Like if you do come back tomorrow, or if you could take a break when you do come back, you know.
Mhm.
Yeah.
Yeah.
Good.
So this is both. Okay.
This has section A and B of winter 2023. You have the winter 2024 one already, but that has both section A and B for winter 2023.
Yeah.
Yeah. Do you have access to it? Did you scroll through and find the
Yeah,
questions?
it just says midterm 1, and then so it should have like it should have both midterms in here.
Yeah, I have the blank
and
copy of A, but I don't have the blank copy for B, section B, unfortunately. So when you practice that, like try to block it out. Yeah.
Okay. Okay.
And you know the first table, the table of reactions, regional selectivity, stereoselectivity? The ones that say none, think of that as both syn and anti-addition for Helix class.
Oh wow.
Yeah.
Okay. Okay.
Yeah, that's good. Okay. Good luck, Gerard. Good luck making your note card studying tonight, and you're gonna crush it tomorrow. Let me know how it goes. How it goes too.
Yep.
Yeah.
Thank you.
Yeah, of course. See you guys. Bye.
Hey, Bryant. I just had a quick question. So, I was thinking of doing the private tutoring that you offer. I still haven't like talked to my parents about it, but like my mom was saying like she would be willing to pay for it if I need the help. And I feel like it would be beneficial for me, like maybe once a week, like just reviewing what I went over that week.
During the lecture?
Yeah.
Right.
So like what is it that you offer for that?
So we could do a 10 session package, and I don't know if you saw my flyer, but that is gonna be $480. But what we can do is we could do a payment plan where you pay half for the first 5 sessions, like $240, and then after we use up the 5 sessions, you could pay the other half after the 5 sessions. After we use up the 5 sessions, if that works better for you, right?
Okay.
And then we could set up a regular time every weekend, like Saturday or Sunday, to meet up and review what you learned over the week, and you send me all your notes that you took, all the practice problems, so that I could look at them, prepare notes and practice problems for us to go over with homework for our session, right? So that's how it'll work. And I'll send you a private Google Drive folder for our notes, our private session recordings, and all the practice that I make for you.
Okay, yeah. Weekends would be great too, because I was gonna ask like what's the best of time you're available.
Yeah, but it would be weekends because the weekdays I have like school, and then like I get home, I'm so tired. I have these office hours too.
Yeah,
so
I get it.
It would be the
I
weekend.
appreciate you going like past time to help us during exams. Thank you.
Yes, of course. Like time flies whenever I tutor, you know. Like I'm like, oh my gosh, is this time already? Like when I'm in the like tutoring, I'm in the zone. Like time flies so fast.
Yeah. But yeah, I will let you know. I will talk to my parents about it, see like
yeah, let them know about the payment plan, like half now and then half after the first 5 sessions.
Okay, so after the first 5 sessions, since like I wouldn't be doing 10 sessions, would I be paying that like based on how many I do after the first 5 or?
So for the 10 sessions, what we can do is we can do 2 sessions a weekend, or if you don't want to do 2 sessions a weekend sometimes, like before quizzes, we could do how many weeks there are left in the quarter. This is week 4. So this week 4, 5, 6, 7, 8, 9, 10. There's 7 weekends left. So we could do 7 sessions instead if that works best for you. Or if you want to stick with 10 sessions, we could do 2 sessions and some weekends to prepare for some quizzes or final.
Oh yeah, maybe the final, like maybe I would want.
Yeah, right.
Sessions. Okay, yeah. I will come back to office hours. I'll try to come back to office hours tomorrow because I do have an exam on Thursday. So yeah, I will let you know.
We'll prepare for that for sure.
Yeah. Okay.
Yeah.
Thank you so much.
Of course, Jana.
Have a good night.
Good night. You too.
Bye.
Bye.